Hello? Okay, perfect. Hi, hello Shanghai, hello China. My name is Armin, and this talk is quite a bit about programming, but more importantly about debugging, and particularly about debugging production things. And so I have to do a little disclaimer up front, which is that I used to do a lot of Python, but I do a lot less now. And so a bit of this talk is inspired by the work that I did the last couple of years, which also involves a lot of other programming languages. But in particular, what it does involve is I want to share my understanding that slower languages actually have some unexpected benefits. So Python is commonly criticized for being a slow language, that there is Go, Java, that there are a lot of languages which are just faster. And this is true, and I'm not going to defend this, but I want to show that performance is not the only thing that matters. There's actually another metric that's kind of underestimated sometimes. So I go on the internet by the name Mitsuhiko. I built Flask, Werkzeug, Ginger, Click, and a bunch of other relatively popular Python libraries. And at the moment I work at Sentry, which is a company that builds an open source project, which is also written in Python. And Sentry actually does play a little bit of a role in this talk, because Sentry is, first of all, my employer, but it's also a company that's focused around crash reporting, which has a lot to do with debugging. And so a lot of people know that I care a lot about APIs, but I also care a lot about debugging. If you've ever used Flask, you know that there's a small little debugger built in, which gives you a stack trace that shows you all the local variables. So anything related to debugging is dear to my heart. And this is a thing that I believe in, which is that developer experience matters. People generally care that things are nice. They like to look at beautiful things. And they also are much more interested as a developer if the environment they're working in has a good experience. And there are many programming languages that got successful primarily because of the developer experience. And Python is one of them. But also, things will go wrong. And when things go wrong, it matters that you can figure out why they go wrong. So the ability to debug is very important. And when we talk about API design, API just doesn't stop with the function calls. API also matters when it goes wrong. It matters when you have exception values that fly, when you have error values. So the information that you can get out of an error is important, and it's part of API design. And this extends to situations where you would expect errors not to happen. So a release environment, when you ship a program to a customer, typically shouldn't error, right? We don't expect errors to happen when a customer runs your application or when a customer interfaces with your application. But errors do happen in production, and that's why it's important that we also understand how errors work in production environments. So this talk is mostly going to focus on errors during production, not errors during development. And so this little example here, I think, is very important. It's very important for the company I work for, Sentry, which started out as an open source project, which was pretty much inspired, I would say, by this line. But it also overall matters to why Python is very, very successful. I don't know how many people are familiar with this concept, but there's a function called getFrame with a little underscore in front of it, which returns what's called an interpreter frame. And this, I think, is, if you show to people an example, if you want to show to people an example of why Python is successful in the web space, in the software as a service space, I think this encapsulates it really well. At any point in time, you can interface with the interpreter directly, and you can extract information out of it. There's a little example that shows you how to use an interpreter frame to access local variables. And this is something that for a long time was unique to Python, and why it was really a pleasure to work with in a production environment, because when things went wrong, you could use the interpreter frames to get more information out of it. And runtime introspection is powerful. It's a very potent tool, and this is what, for me, was for a long time why Python was was a lot of fun to work with in a production environment, but why I could also trust it a lot. But obviously, runtime introspection also comes at a performance cost. And as Python developers, we're generally used to paying this performance cost. But I want to show in this talk that this performance cost can surface in different ways. But at the same time, it's very important to have this ability to work with this. You want to be able to extract this information. And maybe only with workarounds, but this information is important. And the reason it's important is because of this. A lot of people say, when they write a bug report, or when they read a bug report, they try to reproduce it as a developer, and then they cannot reproduce the issue. Because many problems just will never surface on a developer's machine. Because they could be fundamentally a race condition. They could only show up with certain data that you will never have on a development environment. So how do you debug these problems that you cannot debug on your own machine? And the way to debug them is generally to have your debug tools in production. And this is particularly important if the error happens on devices you will never have control over. So just think of, if you build a web application, you have millions of individual browser sessions, hundreds of countries, or people from hundreds of countries working with your website, but there are so many things that can go wrong that you will never be able to reproduce. It could be a specific browser extension that breaks your website. It could be that it only happens for a particular country because an ISP does certain things with the network connection. Or just generally a firewall is deployed that does break something. Or it's a weird time zone issue. Like a lot of websites maybe not expecting that the time zone is off by 30 minutes instead of an hour. So there's all these kind of things that can happen, and you will not be able to reproduce this on your machine, even if you try to recreate it entirely. It gets even harder if it's not just a website. If your code runs on a device that only periodically gets updates, if at all, that you just have no insight into. And you might not even want to update these devices without the input of the person that runs it. There's some moral question on if auto updates on things are okay that people don't even know can be updated. So let's talk about how to debug something in production. And what does this mean? To debug something in production means that we want to use tools similar to a debugger on something that just runs out there. It could be a server process, it could be an IoT device, it could be anything really that runs code. And my company is again a good example from the other side as well. We process a lot of events that come into our system, and these events are being processed by some code. But these events are produced by effectively our customers or the code that they run. And so it's impossible for me as a developer to create a test suite that covers everything that will ever fly to the API. There are so many corner cases that you just cannot reproduce. So for us, it's very important to understand our system in production. And again, this is why we need basic debugging and introspection in practice, in production. So the metric that I want to show a little bit more light on is this idea of production versus debug performance. So a lot of people are very focused on making code fast. And that's good. It's a good thing. But a lot of these optimizations, they are effectively standing on the other side of the debuggability. And so the metric that I think matters quite a lot is how much slower does your code get once you start debugging it. And once we look at this metric, like how much slower does it get once you turn on the functionality you need for debugging it, languages actually score quite a bit different. So I want to talk a little bit about runtimes to show this example, or just generally different programming languages, how they approach this. The most obvious language here to talk about is Python, because it's a Python conference, but also because Python does actually score really well in that it doesn't get much slower anymore once you start debugging it. So there are generally three different types of sort of language runtimes. The most simple one is a simple interpreter. That's what CPython has. The second example would be a JIT-compiled interpreter, like Nodes V8, and then ahead of time compiled like C, C++, something like that. And even if you talk about C and C++, there's still a runtime involved. It's just being statically linked into the same program. C generally gets away with people saying it doesn't have a runtime, but there's a C runtime in there, which does the very basics of what is necessary to run this code. So the next few slides are examples. They are not scientific, and the numbers on them are not really comparable, but I want to give you an idea of what it means to turn on debug. So the first example is an interpreter. This is going to be CPython. So a simple interpreter runs through your code, executes it line by line, more or less, and presents you with the results of the execution. So I don't know if you're familiar with the dis module in Python, but it lets you disassemble a function. And so this function just takes two numbers, it adds them together, and returns the result. You can disassemble this function at runtime. It gives you the bytecode instructions that will be executed, and here we can see two that matter: load fast, which loads a local variable from a certain index, and binary add, which adds two numbers together, and then it returns. So in the CPython interpreter, there's a massive while loop, which has a switch statement in it. And it has a case for every single bytecode instruction that can come by. One of them is called load fast. But what's most important to see here is that what this instruction does is actually quite complex. It fetches a variable from the stack, or it fetches it from this list of variables. Then it does some basic function sanity checks to make sure that this variable actually exists, because we don't want to crash the interpreter if it doesn't. And then it puts this value on a stack. Once we go into binary add, it's even more complex. We have to pop two values from the stack. Then we have to add them together. There's even a micro optimization in there to make it a little bit faster for the common Unicode concatenation. But what matters here from this, you don't have to understand the code. What matters is how much code runs. There's a lot of compiled code. There's a lot of C code that has to run to execute even the most primitive of Python code. And I would guess that CPU cache optimization doesn't matter at all here anymore, because we execute so much code, it will probably never fit on a cache line. And we have so many interactions. So long story short, there's a lot of code. And because of this, it's actually also very hard to optimize Python. You can micro-optimize this evaluation loop, but you cannot really do any significant improvements here. So to demonstrate this a little bit better, this here is three functions. We have one function that just raises an exception. We have another function which basically catches this exception that is being raised from that function. And then we have a third one which does more or less the same, but instead of just catching the error and ignoring it, it starts to capture it and capture the stack trace. So if you call sys.exe_info in Python, this will capture the stack trace. And when capturing the stack trace, in Python we actually capture a lot of stuff that comes with it. We capture local variables at this point in time. We capture all the parent frames. We capture the exception object itself. So you can use this information and render out a stack trace with local variables with everything intact. And this is what matters. The difference between just catching the exception and also capturing the stack trace is only a 7% performance penalty. This is more or less insignificant. Of course, if you want to do something with the stack trace, it's going to get a little bit more expensive. You will have to do something with it. And for instance, sending this stack trace to a remote service for storage is going to slow you down. And there's only limited concurrency you can do to do this in the background. But just catching this down is really cheap. If we go to a JIT compiled language, all of a sudden it looks very different. So V8 is an implementation of JavaScript written for the Chrome browser, and it's also the base of Node.js. And the way this works, as an example, and there are different variations of this, is the JavaScript code will be compiled more or less as it's running into native assembly code. And this is can make much faster additions, for instance, because we don't have to go through the C layer to do some bytecode juggling and working with the data. We can directly emit, well, we know this is an integer, you're just going to add them together with a native addition assembly instruction. So a lot of JavaScript's performance comes from the fact that for as long as we're in an uninterruptible set of instructions, we can just emit relatively fast native assembly code. So again, we have the same example here. We have a function that throws an error. We have the second function that catches it, third one that catches it, and then also accesses the error.stack property. Now that's obviously not the same as calling sysexinfo in Python, because it will only give it a stack trace, but it will format it entirely into a string. So it does different things. But what matters is that this function is the sort of primitive value that we would use to actually debug an error in production. And the difference between running, just catching the exception, and actually building the stack trace is like an 83% performance penalty. This is significant. We're almost an order of magnitude slower by just trying to debug this thing. So if you have a production system that for whatever reason raises a lot of errors and you want to render them out, all of a sudden this will turn a lot slower. With an ahead-of-time compiled language, it also overall looks completely different to work with it. So an ahead-of-time compiled language is something like C, C++, Rust. These are languages which are, before we even start executing, we already have compiled to native binary. And the CPU will just run through it and will execute it. And ahead-of-time compiled languages are primarily fast because they are doing very little between executing the code as the programmer has written it. So when we add two numbers together, there is nothing else that's going to happen here, right? It's just going to be an addition. Function calls can be inlined in a stack tray into another function, so we will not even have something like a frame that we could see. There's definitely no interpreter frame that would tell us where the local variables are. There's very little there. And it typically will follow the system conventions for how to call a function. So if I write a C++ function and that calls another C++ function, that will follow the semantics of how a function call should look like on that operating system. And that matters because if I would want to now instrument this function call, I would kind of have to work against this, right? So the example here will be C compiled with the Clang interpreter to native code, but it already gives us a problem. The example that we had so far was a stack trace. So what's a stack trace in C or C++? How do we get it? Well, there's a runtime in it, but this runtime is very bare bones, so we don't have much to work with here. So the first thing we need to do is something called stack walking. Stack walking is the process where from one instruction that we want to go back, but not to where we came from, but we actually walk to where that function would return if it returns. And then we keep doing this for all the functions that called us. So we start at a certain address and with certain register values, and then we figure out where to go to. But how do we do this? This information is really, well, it does exist in a way, but it's not guaranteed to exist for one. And even when that information exists, it's there for a different purpose. And so there's actually dwarf that helps us with this. Dwarf is, it's a pun on ELF. ELF is the native executable format on a lot of Unix systems. Dwarf was just a joke, but it now has given an acronym retroactively. And this little standard can tell a program how to unwind the stack. But as mentioned earlier, it unwinds to where the function returns to, not to where it came from. And that difference plays a role. So we unwind to where we would return to, and what we get out of this is just more addresses, right? We start out at an address, and now we're going to learn to where that function would return to. What's the line of code executing or the instruction executing after this function returned? And we can do this for a couple of times, and then we have just more numbers. Great. So it's still not the same thing as we would have in Python, where I can see a stack trace. we actually now need to figure out what the functions are called, where that instruction would be in the file. There's more dwarf information I can use for this. But this information is typically unavailable to the program when it runs. A lot of people don't actually have debug information available when they run programs. If you run Microsoft Word on your computer or any binary that you have, that will just be code in there. There will not be enough debug information because the debug information is only kept at the original developer's machine. So for server programs, you could ship your debug information with it, but that debug information can get huge. We have some customers that have a 50 megabyte large executable, but the debug file is 4 gigabytes, right? This is significantly larger. So just getting the stack trace is fast. I give you that. You could build a stack trace quite quickly, and it will probably not impact your performance that much. I didn't even consider benchmarking this, because my point is that doesn't help me, because it's not good, and to make a good stack trace, that would be much slower, right? I would want the function names, I would want to know where it is, and to actually build a stack trace with all that information, that takes a lot of time. Depending on how big your debug file is, that can be multiple orders of magnitude slower than the function that just raised the exception. So to actually do this with production C++ applications is really complicated. Typically, you just unwind the stack trace on your device, and then you send your stack trace with all those numbers to some other service, which goes in and tries to give you the function names. But then, how do I get local variables? How do I figure out what else happened there? Like, just the stack trace is very little information. I would want to know, why did I have the stack trace? Like, is there some other information I can use to help me understand why something goes wrong? And even with this deferred symbolication, there is really just a lot of disappointment when working with stack trace in C++. And most likely, even if you have the stack trace, you can't even trust it entirely. Because as I mentioned earlier, the stack trace is not, it doesn't tell you which thing called you, it tells you where would you return to. And there are a lot of optimizations that the compiler can do where what called you and where you return to are actually completely different things. If you have a tail call optimized function, one function might be missing in your stack trace because it jumps through an entire function. Or if you have inlining, functions will completely disappear out of your stack trace. And how good the system is at actually trying to figure out that an inline happened very much depends on the system you're using. So on Windows, we have PDB files. PDB files are not a lot of fun to work with, are largely undocumented. They only gained support for inline functions a couple of years back with Windows 8, I believe. And so the debug experience you get from Python versus the debug experience you get from C++, there are worlds between. More importantly, and I think this is something a lot of people don't understand, is that if you want a stack trace on anything, you need to make the stack trace when the exception was thrown. So if my exception flies up the frames and is only captured like 5 frames out, for me to understand where the exception came from, when that exception was thrown, someone already had to calculate the stack trace. And in Python, that happens constantly. In JavaScript, at least parts of that happen constantly. But in C++ or in C or even in Rust and other languages that compile to native code, for performance reasons, we often don't capture the stack trace. We only propagate some error codes. So if you have a C function that calls more C functions, that calls more C functions, and the innermost function returns an error code, and that's just being propagated, good luck finding out where it came from in the first place. Like, it could be any function, really. So you would have to read the code, try to understand under what circumstances might this error be returned, but it doesn't tell you where it came from. So the language design does not encourage debugging. So debuggability incurs runtime cost. And so far, we have only been talking about stack traces. But there's a lot more that you would want to understand in a production environment. JIT and ahead of time compiled optimizations, they are the enemy of good debuggability in many ways. For JIT compiled languages, the moment you start doing anything interesting or potentially scary to get some debug information out, you're going to have performance impact. And that performance impact can matter. And the reason why the performance impact matters is because if something gets too slow to what baseline is, then completely different things can happen again. I have a good example here. We were recently looking in a Rust service for a memory leak. And so we only saw this memory leak in production. To turn on a memory debugger, we used address sanitizer, which is the fast one. That slowed down the execution of the program so much that it couldn't execute and finish the task anymore because it hit timeouts. So we couldn't actually do the memory debugging in production because just turning on the debugging made it no longer behave as it was behaving originally. That was never a concern for us in Python because Python is already like baseline performance. That's about as slow as it gets. To debug this doesn't make it much slower. You can do memory debugging, you can do logging, a lot of stuff in Python without negatively influencing your performance anymore. And Sentry, the company I work for, it exists because in Python, which was the first language that it supported, doing what Sentry is doing was easy to do. For us now to build similar support to what people expect from our Python client in other languages is a lot more work. It takes one of our engineers to build, if they would start from scratch, probably a couple of days to write a Python client. We have a team of 3 people. We're working for 4 years now on making C++ stack traces just work at all. It's a completely different world once you start looking into languages that are more complex than Python. To get to something that's not even a tenth of as good as a Python stack traces. And when you build a large service, understanding why it breaks in production is really important. And this is something I think a lot of people they underestimate this, how good of an environment we have in Python. The argument I hear from a lot of people is, well, stack traces are cheap now on every environment. So I want to show you that there's actually more we can do in Python. We get to expect more. This is just an example from the Sentry UI to sort of see what baseline Python looks like. You can see the name of the exception, the value of the exception. You can see where exactly it came from. We can tell you exactly what source code there was there because we can even fetch the source code at runtime from Python without performance impact. If you raise a stack trace in Python without anything installed, just write a script, make an error, Python will show you the source code in between all of the function calls of one line of source. This is built into the language. It was always sort of optimized in quotes for that. It has a caching module built into the system to give you source code. And we can show you local variables. Sort of that's the baseline experience we would like people to have. And only Python so far has that experience. Because getting local variables in any other programming language is almost impossible. So value what you have. Because not a lot of other programming languages actually have this. So what do we have? The first one we have is, I think the most obvious, and I already mentioned part of this before. Python can tell you all the interpreter frames that currently exist. Obviously, we have already seen you can get the one from a current frame, from a current stack, from the current exception. But you can also get it for all the threads which are running on a computer. That are running in your interpreter. So a good example of what you can do with this is if you have web requests, and some of them are really slow, or you have tasks in a task worker, and some of them are really slow, you can use another thread to take care of other threads. And if a thread takes more than 30 seconds to run, you can dump out its stack trace. You can figure out where was this thread after 30 seconds, in which function did it get stuck. Super easy to do in Python, surprisingly hard to do in other languages. Once we have an interpreter frame, we can get all the local variables. We can also get the global variables, but they're not as useful. But this is a super useful feature because we can actually understand which crazy Unicode string went into my function when it got an error. Or what input was sent into it that triggered a miscalculation. Every exception in Python carries its stack trace as of Python 3. So even if the exception was sent through other functions into some logging system, you can still go back and find the stack trace. Super useful. And that stack trace carries a lot of data. And most important, and I think this is completely underestimated, you can monkey patch functions in Python. If I want to figure out something about a thread, I can import the threading module, and I can replace a function on the thread, on the base thread class. So any other thread spawned in Python at this point will use my new start method instead of the original start method. And I can use this for a lot of things, like I could register every thread that's being started somewhere by category. I could name it. I mean, there's already a name on it, but I can name it in different ways. I could give it another description. I could start doing performance metrics on this. I can propagate some distributed tracing systems through all my thread calls. And this does not make it any more slow. As fast as Python threads starting are out of the box, this adds such an insignificant performance overhead to it that most debug systems will actually start patching these things. So if you ever use New Relic or a system like this, which captures performance metrics out of your program, what they typically do is they import a whole bunch of really common modules in the interpreter, and they will start intercepting these. I don't know how many of you are aware of this, but at least from a technical level, if you already have a running Python process somewhere, you can attach GDB to it, suspend the program, run the Python C API to execute custom Python code, and open a reverse shell so they can SSH into your process and then run a Python shell on it. It does require a little bit of glue code, and there are various modules you can find on the internet that will do this. But on a technical level, the interpreter gives you all the tools necessary to attach to an already running process. So even if that process was started 3 years ago and you don't want to restart it, the process shows a bug, and now you feel like your debug tool is not in the code that you can run it, there's still ways to get into it. Python 3.7 has a cool new feature called context variables. This is actually more or less an execution context. So if you're familiar with .NET, in .NET there's a logical thread of execution that you can follow even through asynchronous calls. In .NET it's called, I think it's called execution context. We have this now in Python 3, which means that even if you spawn an async function that goes through various different code paths that are very complicated to follow, you can propagate something like thread local information through all of these. So if you want to do performance metrics and you want to understand how every of these async calls behaves, there's enough tooling that the interpreter provides for libraries to hook into. Obviously, I think as people build more SaaS applications, as people build more IoT devices, people will want to have more ability to debug stuff in production. And because a lot of these services are now written in languages like Go or Rust that are ahead of time compiled, I believe a lot of these languages will actually start to slowly add functionality that we have already had in Python for many years. Obviously, a Rust, a C++, they will never have local variables in a production system. That would completely destroy all the performance that you have. But they will start to get closer and closer to being able to debug in production. But because of that, we have a huge history in Python of being able to debug these things in production. And we should really value this. If we use a language that has a performance, it is slower than some other competitive language, but we get all these tools for it, then we should use them. We should take advantage of what we pay in performance penalty to. And because of that, Python is still a really solid choice for service applications because of this debugging. And with that, feel free to ask your questions. Also, I want to say that if you have questions that sort of only tangentially related to this talk, also take the chance to ask them, because I'm not that often in China.
Thanks, Armin. 我们还是2个问题，然后。
OK， 我们有2个提问的机会。OK， 这边一个，这边一个。
I remember you have shown a monkey patch the thread start function. Yeah. And I want to know if you can get the source code about the dynamic generated code, like you make a new start. Can you get that? I'm curious.
So The answer is complicated. So it depends a bit. In Python, there is a system called custom loaders. And if you have code running that loads things at runtime, you can use the custom loader if it was provided to get the source code. So for instance, Jinja templates are at runtime generating Python code. And Jinja also exposes under loader. So if a traceback system tries to figure out what's the source code of the Jinja template, they can use the loader to look up the original template source. So even if you use a string created at runtime, the loader can give it a source code. However, if you use your own system that generates code at runtime and you don't provide a loader, then you won't be able to see this. So a lot of these debug systems actually require a little bit of cooperation from the developer.
OK， 我们最后一个问题。
There's one over there, on the right.
OK。
I get your points. The interpreter language has much context in runtime, so it's very easy for us to debug in production and has less performance penalty when debugging. And the GIT has less, the AOT has the least. So I wonder if we could reach a sweet spot that a language it has a good performance and easy to debug in production, has much debug information. Yeah. So I wonder, can we reach a sweet spot that a language has a good performance and much debug information?
So I didn't quite understand the question. Can you just summarize it?
I wonder if we could reach the sweet spot that a language has good performance and and easy to debug in production.
So when it comes to finding a balance between fast code and debuggable code, there are different languages that draw the line somewhere in the middle, but in different ways. So for instance, if you have a good example here would actually be another Python-inspired language, which is Cython. Cython compiles Python-like code to C, but it still does it on high-level function calls. So each function call in Cython costs money in performance. And these function calls are actually represented so that you can see them in the stack traces. In C#, you actually have a lot of functionality in the runtime environment to do a lot of runtime introspection. And then only if you start using that, it turns slower and slower. But where these performance degradations are okay or not really depends on what you're building. Like if you build a machine learning system and it requires really fast execution, and now you want to start adding debug functionality to something that otherwise just executes C code, would probably be unacceptable, right? So it really depends. Like right now, I think Python has a pretty good spot for service applications, because not a lot of other languages have even basic functionality on that level. But it's really hard to say if there will be languages that give you as much expressive power and still perform fast.
OK, that's all for the questions. Thank you, Armin. Thank you for the talk.